We now begin Module 8 in the last module, the last chapter of my course on random processes and Kalman filtering. In Module 7, we did the Kalman filter. And if you recall, the Kalman filter was based on linear dynamics. That is a system of linear differential equations. And when that was the case, and with the other assumptions on the noisy inputs, the Kalman filter was the best linear, unbiased estimator there is, where best meant minimum mean square error. What do you do, though, if you don't have linear dynamics? And that's going to become the extended Kalman filter. I mean, that is one way to approach nonlinear dynamics, is to still use something that kind of looks and operates like a Kalman filter, but it's not really the Kalman filter. And I'll get into this later, but when we do that, we lose optimality, or there's no guarantees of anything being optimal in that case. But it turns out it worked in a lot of cases. Anyway, we'll talk about, so this module is really about the extended Kalman filter, but it's based on the concept of linearization. So I first need to talk about that. And it's all based on Taylor series, good old Calculus 101 stuff. It says if you have this function, it can be expanded this way, where you pick some particular x sub 0 in this guy's domain, and here's how to do it. It's an infinite sum. But if you pick off these first two terms, notice that everything, all these x zeros, these are going to be constants. That's a constant. The function evaluated a point at a constant. Its derivative is a constant. Its second derivative, yada, yada, yada. So x is the only thing that's going to become, here you're going to get some x squared terms, but in only the first two terms, it's linear. You have a linear approximation to a nonlinear function. That's what it's all based on. Like in this case of a pendulum, here's the real differential equation that describes the dynamics, but it's nonlinear because of the sine term. If you expand sine term around the operating point 0, which is straight down, here's the Taylor series for that sine, which amounts to, it's just the angle itself, it's theta itself. So that here is a linearized version of these dynamics. And we use 0 because it's an equilibrium point. That's where it's going to oscillate about. So you'd think that your solutions to this linearized equation would be better, closer to when it's only swinging close to the equilibrium point. If it swings too far out of that, this approximate equation, the solutions to it won't be as good as the real equation. So anyway, small angle approximation is linearization. That can be extended to functions of more than one variable and functions that are themselves more than one function, the vector of functions. So where the analog to the linearized version of the Taylor series, the first two terms, would involve matrices and vectors, like here and there, and here's how to calculate them all. I'm not going to get into all that, but if it's all based on first partials, if you take partial derivative, you're okay. Just the first partial. And And I'll quickly put one little application of this is something called error analysis. You've got an input-output relationship, say some output y, in this case a scalar, but it's a function of a whole bunch of inputs, vector of n inputs. You use the formulas on the previous sheet. You can approximate or find the variance of the output based, if you know the variances of the inputs, and there's zero mean errors, by all these, using these partial derivatives, taking the partial derivative of a function with respect to each individual variable. And you can find the individual you can do sensitivity analysis. How does the output change with a small change of input? And again, it's this first partial where you have to use a particular operating point. You got to pick some certain x's, and then these will be approximations around that particular operating. Here's a simple example. You actually measure the slant range, this guy here, and the elevation angle, but you're interested in this horizontal range. What's the sensitivity of the horizontal range to the slant range? Well, it's this partial derivative, which here's the simple geometry, how the horizontal range relates to slant range and elevation angle. Well, this sensitivity is the cosine of the elevation. The sensitivity of the horizontal range to the other thing you measure, angle, elevation angle, is this partial, which ends up being minus this altitude. So you have a way, by using the formulas above, to calculate the variance in the horizontal range as a function of these other measured things, or the geometry of the situation, and the measurement variances of the things you measure, slant range and elevation. In my 29 years of in the aerospace and defense industry, this error analysis was one of the most common methods of analysis. Used all the time, used often, and yet I don't think it was ever taught in college explicitly. How to find the output variance based of a nonlinear situation based on input variances. It's pretty easy and it's very useful. I just didn't see it taught, so I thought it was worth mentioning here. But after this, we'll get into the extended Kalman filter itself. Now that we've talked about basic linearization. That's it for this video.